November 3rd, 2025. While the world sleeps, something impossible is happening at Venus. An interstellar visitor is delivering a package that shouldn't exist in one of the solar system's most hostile environments. This isn't science fiction. This is happening right now, 97 million kilometers from Earth. Venus, where Soviet landers melted within hours, where temperatures can melt lead, where clouds are made of battery acid. This Venus just received organic molecules, water and refined metals from an object that spent 10 billion years travelling through interstellar space. And instead of being instantly destroyed, these materials are surviving, persisting, transforming Venus's atmospheric chemistry in ways we're only beginning to understand. The visitor arrives. Let me take you back 3 weeks. The Interstellar Comet 3I Atlas, the same object that passed Mars on October 3rd, is making its second close approach to an inner solar system planet. The distance, 0.65 astronomical units, roughly 97 million kilometers, close enough for Venus's gravity to capture material from the comet's coma, the thin envelope of sublimated gas and dust surrounding its nucleus. But here's what makes this different from the Mars encounter. Timing. Mars presented a cold, inert surface where materials froze in place. Venus has an atmosphere 93 times more massive than Earth's, wind speeds reaching 100 meters per second, temperatures at cloud level ranging from 0 to minus 60 degrees Celsius, and most critically sulfuric acid clouds that are both incredibly corrosive and paradoxically capable of preserving certain molecules we never expected. What the comet carried by early November 2025, 3I Atlas was still ejecting massive quantities of material, water at rates exceeding 120 metric tons per hour. That's the equivalent of a fully loaded commercial jetliner every hour and a half. But water wasn't the only cargo. Hydrogen cyanide, 80 grams per second, orders of magnitude higher than typical comets. Carbon monoxide at similar rates. And something nobody predicted, spectroscopic evidence of refined nickel, separated from iron through natural processes that mimic industrial chemistry. Venus's gravitational field captured a fraction of these materials. Estimates suggest between 3 and 10% of nearby outgassing material intersected Venus's capture zones. That's roughly 3 to 12 metric tons of water, 1.2 to 1.8 kilograms of hydrogen cyanide, and 50 to 110 grams of refined nickel. These aren't equilibrium components, they're perturbations, foreign chemistry that hasn't been part of Venus's system in billions of years. And the moment they arrived, Venus began responding. The architecture of Venus. To understand what's happening now, you need to understand what Venus actually is beneath the simplified descriptions. Venus's atmosphere isn't a uniform layer of acid. It's a vertically stratified system with distinct chemical zones. Start at the top, 60 to 70 kilometers, altitude, the upper cloud layer. Sulfuric acid droplets here are relatively dilute, 50 to 75% concentration. Temperatures hover around 0 to minus 20 degrees Celsius, cold enough for water to condense into ice crystals, cold enough for certain organic molecules to remain stable. Drop to 50-60 kilometers and you enter the middle cloud layer. Acid concentrations increase to 75 to 90%. This is where most visible atmospheric features occur, the Y-shaped pattern spacecraft cameras capture. The chemistry here is more aggressive. Molecules that survived above begin breaking down or transforming, and this is where the comet's materials didn't just arrive at one location. They entered a dynamic system. Wind speeds of 100 meters per second create superrotation. Clouds circle the entire planet in just 4 Earth days. Materials introduced anywhere are immediately caught up and begin spreading globally. The chemistry of survival. Breaking the paradigm, for decades, the scientific consensus was absolute. Venus is sterile. Anything organic gets instantly destroyed. Venus represents the opposite of habitability. But here's where everything changes. Research published in March 2024 tested 20 amino acids, the building blocks of life, in sulfuric acid solutions mimicking Venus's clouds. The hypothesis: most would be destroyed. The result: 11 showed complete stability. 8 more survived in recognizable altered forms. Only 1 broke down completely. 19 out of 20 amino acids can persist in Venus's clouds. These aren't exotic molecules. These are the building blocks of life as we know it, and they can survive in battery acid hydrogen cyanide's transformation. When hydrogen cyanide from the comet dissolved in Venus's dilute sulfuric acid, it didn't vanish. It began a cascade of transformations. HCN reacts with water, breaking down into ammonia and formic acid. Ammonia is a base. In an overwhelmingly acidic environment, bases neutralize acid locally. They create microenvironments within droplets where pH is elevated, where chemistry that couldn't occur in pure sulfuric acid becomes possible. The sulfuric acid droplets become chemical reactors. Each contains a mixture: sulfuric acid, water, dissolved organic molecules from the comet, ammonia, formic acid, and trace nickel compounds. Each droplet is isolated from its neighbours, a discrete reaction vessel floating in the atmosphere. This creates massively parallel chemical exploration. Billions of droplets simultaneously testing different reaction pathways, producing different products, exploring different possibilities. Some droplets produce nothing of interest, but some might stumble onto pathways that produce complexity. The nickel catalyst. Now we arrive at the ingredient that makes this unprecedented catalytic nickel. When refined nickel entered Venus's clouds, it didn't arrive as a passive element. Nickel is one of nature's most effective catalysts. Catalysts provide alternative reaction pathways requiring less energy. In Venus's clouds, nickel catalyzes several critical reactions: the water-gas shift reaction, carbon monoxide plus water-producing carbon dioxide plus hydrogen. Under normal circumstances, these could coexist indefinitely, but with nickel present, the reaction becomes viable. The hydrogen produced is significant. It's extremely light enough to escape Venus's gravity if it reaches high altitudes. But before it escapes, it's reactive. It can participate in reduction reactions, altering other molecules, creating compounds Venus couldn't produce without this catalyst. Nickel also catalyzes Fischer-Tropsch-type reactions processes, where carbon monoxide and hydrogen combine to form longer-chain organic molecules. In droplets where concentrations are elevated and temperatures favorable, more complex organics can form. Molecules more sophisticated than the simple precursors delivered by the comet. This is precisely the role nickel-containing enzymes play in Earth biology. Enzymes use metal ions at their active sites to accelerate reactions. Venus's droplets don't have enzymes, but they now have nickel ions that can perform similar catalytic functions. The atmospheric response, circulation and distribution. The materials didn't stay where they arrived. Venus's superrotation immediately began redistributing everything globally. Within hours, materials were carried hundreds of kilometers. Within days, they had circulated around the entire planet. But circulation isn't just horizontal. Venus's atmosphere exhibits strong vertical circulation driven by Hadley cells. Warm air rising at the equator, flowing toward poles at high altitude, descending at higher latitudes. This couples with superrotation to create three-dimensional mixing. Over days to weeks, circulation distributes materials throughout the atmospheric volume, though not uniformly. Downwelling zones where air descends can accumulate higher concentrations as materials are brought down from altitude and concentrated by compression, photochemistry and transformation. While circulation spreads materials, photochemistry begins destroying them. Solar ultraviolet radiation breaks chemical bonds, creating reactive radicals that form new compounds. But photodissociation doesn't mean instant elimination. Water molecules photodissociate into hydrogen and oxygen atoms. Hydrogen cyanide breaks down into cyanide radicals and hydrogen. But the reaction products are often as chemically interesting as the original molecules. They can recombine with other atmospheric constituents to form entirely new species. The timescale for complete photochemical destruction is weeks to months. During that window, organic chemistry is active. Droplets enriched with cometary organics are circulating, reacting, potentially assembling complexity before UV radiation ultimately breaks everything down. The unexpected persistence. By late November 2025, several weeks after the encounter, something remarkable is occurring. The chemistry hasn't simply returned to normal. The stable amino acids are persisting. The catalytic nickel remains active. The microenvironments created by ammonia neutralization continue supporting reactions that don't normally occur. This is no longer the Venus atmosphere of early November. It's a perturbed system, temporarily exploring chemical pathways it hasn't accessed in geological timescales. Small changes, parts per billion concentration increases, but in a system as dynamic as Venus's upper atmosphere, even small changes propagate. The question becomes, what is Venus producing with this chemistry? Models suggest several possibilities. Small peptides formed from amino acids linking together, nucleotide precursors assembling from HCN-derived products, perhaps even lipid-like molecules from organic acid reactions. None of this constitutes life, but it represents complexity, chemical structures more sophisticated than simple precursors, exhibiting organization and patterns that don't occur in random mixtures. It's the chemistry astrobiologists study when trying to understand how life's building blocks emerge. The broader implications: Mars vs. Venus. Two worlds, one delivery. While Venus transforms its cometary delivery through active chemistry, Mars takes a different approach. The materials that arrived at Mars in October remain largely unchanged, frozen into the cold regolith, waiting for human technology to excavate them. Two planets, same source, radically different responses. Mars is a preservationist, archiving whatever arrives for future disturbance. Venus is a processor, immediately integrating and transforming external inputs through active atmospheric chemistry. Neither response is better or worse. They're different strategies for handling chemistry that isn't in equilibrium with existing conditions, and both responses are being documented by spacecraft and ground-based telescopes. The astrobiology question. This encounter raises a profound question. Could Venus's clouds support not just complex chemistry, but the precursors to something more? For years, scientists have speculated about hypothetical microbial life in Venus's clouds. Not because sulfuric acid is friendly, it's not, but because specific conditions mirror parameters life requires. The main objection has always been chemistry. What would microbes eat? Venus's atmosphere doesn't naturally contain organic molecules in meaningful quantities. But if Venus regularly receives organic chemistry from external sources, comets, meteorites, interplanetary dust, the clouds would have access to raw materials. 3i Atlas just delivered a substantial pulse of exactly those raw materials. If hypothetical microbes exist, they've just received food. If they don't exist, which is far more likely, the chemistry that could eventually lead toward life has been seeded. This doesn't mean life will suddenly appear. The gap between complex chemistry and actual biology is enormous. but the gap is smaller now than it was before November 3rd, and Venus is demonstrating that atmospheric environments can support more sophisticated chemistry than we previously thought possible. Looking forward, the next 18 months, we're standing at a specific point in time. The observations have been made, the data exists, and over the next 18 months, speculation will give way to confirmation or refutation. By January 2026, the first scientific publication should appear. Papers addressing whether atmospheric composition changed measurably, whether HCN or CO signatures were detected, what cloud droplet measurements revealed. These papers won't answer every question, but they'll establish the observational foundation. April through June 2026 brings synthesis and modelling. Researchers will build computational models exploring what the observations mean. How long should materials persist? What product should form? Models and observations will constrain each other, building a complete picture. The profound truth. Here's what we know for certain. A comet from beyond our solar system passed through the inner planets in October and November 2025. It carried materials forged in another stellar environment billions of years ago. It delivered those materials to Mars and Venus, two worlds with radically different environments. Those planets are now processing that delivery, Mars slowly through storage, Venus rapidly through chemistry. Both are teaching us about planetary systems, about chemistry under extreme conditions, and about how complexity emerges when worlds receive chemistry from beyond their own systems. The chemistry doesn't wait for our instruments to be ready or our papers to be published. It proceeds according to its own rules. Right now, as you watch this, Venus's upper atmosphere is circulating molecules that have never been part of its natural system. Reactions are occurring that haven't happened there in billions of years. Chemistry is exploring pathways opened by an interstellar visitor. We live in an extraordinary time, an epoch where we have eyes throughout the solar system, watching as an interstellar object interacts with our planetary neighbours, where we can document chemistry unfolding on other worlds, where we're learning that planets are far more dynamic, responsive and chemically creative than we imagined. The comet has passed. The delivery has been made, the chemistry has begun, and over the months and years ahead we'll watch as two worlds reveal what they've done with their gifts from interstellar space. This is November 2025. This is happening now, and you're witnessing the beginning of a discovery that will reshape our understanding of planetary chemistry, atmospheric habitability, and the potential for complexity to emerge in the most unexpected places. Stay curious. The universe has more surprises waiting.